Okay, so what is angular momentum? We'll look at that first. We know that angular momentum is shown as capital L, and the initial equation we have is m r perp v, where m is the mass of the object, that is from the center. The r is the perpendicular r, which we'll go into more detail in a second. And the v is the velocity at which it's moving. So, what is the r perp? The r perp comes from the loop shortcut, which generally means that, let's say we have this ball, this one you'll see in one of your homework problems, where the ball is going to be falling, and this is the axis of rotation, and this is our little flagpole. So generally what you'd think at first is the r would be the L, the length of our flagpole, but when using the loop shortcut and in angular momentum, you'll know that instead you need to use the perpendicular r, which is right here. So for any term, like in any application of angular momentum, you'll always use r perp. So what is another way to use this, a better way to use this whenever we're dealing with terms such as omega and alpha and theta? Another way we can do this is say, well, let's start off with L is equal to m r perp v. We know that our bridge equation for v is equal to r omega. So if we plug that in, we can say m r squared omega is equal to L. And then we also know that the summation of mr squared is equal to I. So if we can plug that in, we'll be left with L is equal to I omega, which would be definitely more convenient in certain types of problems. So what is the application of this? We already know two forms of conservation. So we know that Pi is equal to Pf. We know conservation of linear momentum. Linear. But we also know that EI is equal to EF, which is energy. But with angular momentum, we finally have the third piece, and we know that Li is equal to Lf, which is something that you'll be using in a majority of the problems you'll do during this section, and also something we will use in just a second.
Okay, an application of the conservation of angular momentum can be seen through this problem. The problem is a space station shaped like a giant wheel has a radius of 100 meters and a moment of inertia of 5 times 10 to the 8th kilograms per times meters squared. A crew of 150 are living on the rim, and the station's rotation causes the crew to experience the acceleration of 1g. When 100 people move to the center of the station for a union meeting, the angular speed changes. What acceleration is experienced by the managers remaining at the rim? Assume that the average mass of each inhabitant is 65 kilograms. So the first step in solving this problem is determining the unknowns and givens. So the givens are the moment of inertia, which is 5 times 10 to the 8th kilograms times meters squared. The centripetal acceleration, which would be equal to g, which is also equal to 9.81. The initial mass before the 100 people move to the center of the station, which is going to be equal to 9,750 kilograms, and then the mass final once the 100 people have moved to the center, which is then 3,250 kilograms, and then we know the radius of the space station is 100 meters. The unknowns are the omega, the initial omega, which we can solve for, and then the omega final. So how we want to start this is looking at just Li is equal to Lf. Okay, and we know that Li is, L is equal to I omega naught, which would also then be equal to I omega final. And what changes the angular speed would be the change in inertia as more people go to the center of the craft. So this is then becomes I naught and I final. So further expanding this, we know that then I will be equal to the I center of mass of the station plus then the mass at the rim of the station times the radius squared. And this is just the form of the parallel axis theorem. So then by plugging that in, we then get I center mass of the station plus the initial mass r squared omega naught will be equal to the inertia plus the mass final r squared omega final. Oops. Okay. From there we can then divide over our final inertia to get then omega final is equal to Ri center mass plus m naught r squared omega naught divided by I center mass plus m final r squared. And we know so what we now need to determine is the omega naught, which we don't really know because it isn't given well. So we know that AC. Okay, so in order to determine the omega naught, we can say that AC is equal to R omega squared, and this omega squared would be omega naught squared. And then isolating for omega naught squared, we can then find that omega naught will be equal to the square root of our AC divided by R. And because we know that our AC is equal to then G, which is 9.81, divided by our radius, which is 100 meters. So we can then determine that our omega naught is 0.313 seconds inverse. And that's what we'll plug in for omega naught. So by plugging in, so now we're going to plug in all our knowns. So we have then our 5 times 10 to the 8th plus then our mass initial, which is 9,750 kg times 100 meters squared times our omega naught, which is then 0.313 seconds inverse, all divided by 5 times 10 to the 8th kilograms meters squared plus then our mass final, which is then 3,5 kg. Okay, so now that we've plugged everything into your calculator, you should then get the omega final should be equal to then 0.35351 inverse seconds. And in the problem it's asking for the acceleration of the actual acceleration at the rim of the space station. So in order to do that, we then go back to AC is equal to R omega squared, and then we say that then we're looking at the new acceleration, so then it'll be R omega final squared, which is then equal to 100 times 0.315 inverse seconds, which would then get our new acceleration at the rim to be 0.315 12.32 meters a second squared. Woo.